So good afternoon to all of you. Good day. Those of you who might be in a different time zone. I'm Hazel Siv, Dean of the College of Science here at Northeastern University, and it's my enormous honor to welcome you to the Nath Distinguished Lecture, the first Nath Distinguished Lecture. There are two, yes. I love that. That is the first of many rounds of applause that we will give here. There are two honors that I have today. One is honoring this new lecture based in the Northeastern University Physics Department, led by Professor Mark Williams. And the other is the honor of welcoming today's speaker. Today, indeed, marks the start of a new era, the Nath Distinguished Lecture Series. The lecture seeks to celebrate discoveries and significant advances at the frontiers of physics. And it's with enormous gratitude that I acknowledge the series is enabled by the generous contribution of Professor Pran Nath and Dr. Shashi Nath through their love for Northeastern University and the physics department. Thank you with all my heart. Pran Nath is a renowned, award-winning theoretical physicist with a research focus in elementary particle physics. He is George and Kathleen Waters Matthews University Distinguished Professor and holds the distinction of being Northeastern's longest-serving professor. That is really quite an extraordinary accolade, Dr. Nath. Dr. Shashi Nath received the PhD from the University of Chandigarh and has been associated with Northeastern for many decades as a valued and beloved teacher. Thank you so much, Shashi. And how you have seen this university evolve from its beginnings as a blue-collar place, university that enabled the education of so many students in the area, through its rise, through its development as an R1 university, an ambitious university, the innovation capital of academia, I call Northeastern, how you have seen the physics department grow and change and become so distinguished with many distinguished alumni, students, and faculty. What an extraordinary change, what an extraordinary development Northeastern University has had. And I know it is very close to your hearts and you are filled with love for this place that has been your home for so many decades. Thank you so much. Nath's area is in supergravity, where he developed the first supergravity theory and has gone on to be a leader in the fields of applied supergravity and supergravity grand unification theory. In particular, Professor Nath is credited with modeling minimal supergravity, or M-sugra. Being a life scientist, I had to look up supergravity. And for those of you who also may need a little tuition, I learned that supergravity combines principles of general relativity with those of supersymmetry, another term I had to look up. Supersymmetry suggests that for every known particle, there exists a partner particle with different spin properties. How fantastic, how pioneering, how exciting. I think particle physics, the fundamental building blocks of the universe, is one of the most fantastic fields around. The pioneering work of Pran Nath is today driving discovery at Fermilab and CERN, to which many top members of the Northeastern Physics Department contribute. Pran and Shashi, you are truly emblematic of Northeastern excellence and belonging into the Northeastern University family. For almost 6 decades, you have been part of the extraordinary evolution of Northeastern University and the Department of Physics, from its fledgling beginnings to the high impact and ever-rising reputation we have today. We thank you for your wonderful contributions, your engagement, and we congratulate you with the greatest respect. Please join me again in thanking and congratulating Pran and Shashi Nath. And now it is my pleasure to introduce the inaugural speaker in the Nath Distinguished Lecture Series, Dr. Yuhai Tu. Dr. Tu is a physicist at IBM Watson Research Center, recognized for pioneering contributions across multiple scientific domains, and I can attest to that. I will tell you what I did in a moment. But let me give you a little background so you have it. Dr. Tu graduated from the School of Gifted Young at University of Science and Technology in China and received the PhD in theoretical physics from UCSD, later joining the IBM Watson Research Center. His groundbreaking work on collective phenomena in active systems earned him the 2020 APS Lars Onsager Prize, the highest honor in statistical physics. Dr. Tu's current research focuses on the dynamics of biological networks, thermodynamics of information processing in biological systems, and statistical physics of machine learning. Dr. Tu's lecture, entitled Physics for Deep Learning Towards a Theoretical Foundation, promises to explore the connection between physics and artificial neural networks, particularly timely following the 2024 Nobel Physics Prize awarded in this field. The presentation will provide, we are told, an introduction to artificial neural network-based machine learning and will share progress in developing frameworks based on statistical physics and stochastic dynamical systems theory. Is that true? That is true.
Remain to be seen.
We anticipate. Dr. Tu, I took a look through Google Scholar at your publications and was enormously impressed by the breadth of your scholarly considerations and achievements. As a life scientist, as I've mentioned, I am deeply interested in how living systems are built and function, and I find your work relating this to physics and biophysics fascinating and important. Thank you for visiting Northeastern today. Congratulations on your achievement of being the inaugural speaker in the Nath Distinguished Lecture Series. Welcome to Northeastern.
Thanks. All right. Okay. Thank you for that wonderful introduction. I hope you get half convinced by the end of my talk that I deserve all these praises, and thank for you for enabling this. So I'm very excited to be here. I was here before, and also let me just tell you a little bit of story of my connection with Northeastern. I think my name came up because, probably suggested by Herbie. Herbie Levine was my seat supervisor by my days in UCSD. So, and Herbie and I did not work together after I graduated from PhD, but recently our common interest in AI and machine learning brought us together. So for more than 30 years after I graduated, we wrote the paper together last year in PNS about the physics and machine learning, a two-way street. So I was very happy to be reunited again with Herbie on this new endeavor. So I'm gonna tell you a little bit about that. And the backdrop, as you were told, is obviously on everybody's mind is the Nobel Prize in Physics awarded to John Hopfield and Geoffrey Hinton last fall. And this caught many people in surprises for many reasons, but also, again, it's not that surprising. So, just bragging a little bit. So in this paper that we published together with Herbie last June, that was all because before neural network, before this Nobel Prize, we said about the two-way street, right? So this two-way physics for machine learning and machine learning for physics or physical sciences, right, in general. That's in June. That was published in June. In fall, there were 2 Nobel Prizes awarded to one in chemistry, one in physics. The physics is the topic of today. The physics was awarded to Jeff Hinton and Hopfield for their foundational work, underlying neural network, and its importance to machine learning, right? So that's one way. Physics actually contributed to the development of a type of neural network, as we will see, right? But what is the other Nobel Prize? That was in chemistry. That's the other way around, right? That's how machine learning has helped protein folding. There's an AlphaFold. That was the other direction that we talked about in that review our introduction article. So by the time they announced the award, I sent a text to Herbie. I say, 2 for 2, right? So we didn't intend to make that prediction, but indeed it happened. Okay, so we were very excited about this, of course. Okay. Okay, let me go back a little bit.
Keep talking. I'm sorry.
Okay, no.
I
So
couldn't see.
So why is physics important for neural network or to machine learning? Let's just make that a question in mind for now. Let me go through a history of what I see as the development all the way leading to the current day deep learning, right? So everybody, unless you live under a rock for the last 10 years, you would know about what ChatGPT and AI and the neural network, that's all about. But you wonder also how come physics is awarded to a physicist in the physics, Nobel Prize in physics. So here's some little bit of a history, maybe helping you try to understand that a little bit, right? Okay, so in my mind, there's really 3 waves of neural network development, right? The current day neural network model, artificial neural network model, originated very, very early on. So the sort of inaugural paper for that topic really is dated back all the way back 1943 by these 2 gentlemen, McCollum Pitt, in a rather obscure. So let me move on. So that's the wave number 1, right? And then that was the first wave, which lasted until the high point of the first wave, which really is the perceptual machine. And then the so-called winter of AI, the first winter of AI, happened, and then that was the first wave died down at the end of 60s and early 70s. Then there was a second wave. That's the championed by people like Hopfield and also Hinton. People also ask why Hinton is awarded the prize in physics. If you look at the citation, Hinton didn't get the award because his later development in deep learning, in the current day deep learning, it was because the side work was Boltzmann machine. That's the first generative machine you build based on ideas from physics. The name said it all. It's about Boltzmann distribution coming out of a physical, based model. So that was the second wave. It also died. I'll tell you the reason it died. So Hinton was really one of the only people that actually linked the second wave and the third wave. So then the third wave started when deep learning neural network first won some big machine learning contest. In this case, ImageNet. Millions and millions of images. You just want to predict the identity of the image. And ImageNet, everybody's using different type of machine learning tools and algorithms to try to beat each other, compete with each other. Every year they have this conference called NeurIPS right now, but it was called NIPS before. And during NIPS in 2012, ImageNet, the machine learning algorithm called AlexNet. So AlexNet was the first award-winning deep learning algorithm that beat everybody else by a large margin. This model, AlexNet model, was based on a neural network other than other type of machine learning algorithms. So that was the advent of this. So at that time, people realized, yes, neural network is really, really powerful. And then the development since that day is actually revolutionary. So it actually changes touches every corner of our society, scientific research, right? Nowadays, if you don't talk about machine learning, you're out, which is kind of sad, but it's true, unfortunately, in that sense. All right, so that was the third way. So for the sake of the talk, let's go into diving a little deeper into the first wave. So what is neural network? A neural network is a network of neurons. And then you ask the question, what is a neuron in this artificial neural network? What is the operation of a neuron? Well, in the middle, you have the neuron, the big blue dot, and you have this arrow going in, right? These are the input from other neurons. Other neurons will send information or signals, X1, X2. The end of them, each one of the input neuron will send a signal X of I. And then there's also an error. On top of the error, you have a weight, W. That's called weight. So you multiply the input with the weight, and you sum up all the input, right? So that's what operation Z give you a linear sum of all the input weighted by the W, right? So that's the weights. Now you have a Z. Now, then from Z, you have an output, which is a function. They have output Y, which is a function of Z. And this function is a nonlinear function. The previous adding and summing and multiplying, those are linear operations. So this is a nonlinear part of the nonlinear neuron. And that's it. And this Y will then serve as input for neurons downstream, right? And so on. So that's, if you have this operation, the next thing you do is to link them together in a particular way. And in the original paper by McCullough and Pitt, they used it to do logic, right? So very simple logic operation. But this general idea that you can use such an operation to do computing is very profound, right? And quickly picked up by people. So next milestone along this line of thinking is the so-called Rosenblatt perceptron machine. Rosenblatt in the 50s, he took this idea. He says, well, okay, I have this machine built out of neurons and the connection. And if you put them as a layered way, I have a very clear way to interpret what they're trying to do. So the input is a layer, is the input layer. I can put a hidden layer, and there's an output layer at the very end. Tells me, for example, the input layer can just encode information about the input, let's say an image. Every pixel in your image can be a component of the input, right? And the output will tell me, oh, this is a cat, or this image is a dog, based on the pixel information, right? So all the computation can be done either with hidden layer, right? Or in some extreme cases, you don't have a hidden layer, just no hidden layer, just directly from input to output, right? For simple tasks, you can do that. So he actually have he has to build 3-layer network in hardware, because at that time, computing is so primitive, you can't possibly do very large computing, even at this level. So he actually did it by developing hardware. I think it's called Mark I perceptron. So this picture is not a fake picture. This is a real picture where he's standing in front of this machine, actually, do computing with, this is the number, array of 400 photocell arranged in 20 by 20 grid, and a hidden layer of 512 perceptrons, an A unit, and so on. So he actually built the machine that does the work. It was so fantastic that you have this machine, you're feeding an image, it tells you it's a cat or a dog or something like that. It's very, very impressive. So the society is very excited about it. And if you read the right, this is the true article from New York Times, 1958. I'll let you read it. If I don't tell you the year, you were thinking that they're talking about today, right? So this research was supported by US Navy. So he says, well, Rosenblatt made statement about the perceptron that caused a heated controversy among the fledgling AI community. It says AI, I didn't make this up. This is all word by word, okay? And based on Rosenblatt's statement, he made some statement, the New York Times reported the perceptron to be the embryo. They were being tried a little bit cautious and modest. It's an embryo, okay? It's not a fully developed AI. It's an embryo of an electronic computer that the Navy expect will be able to walk, talk, see, write, reproduce itself, and be conscious of existence. So basically, they are building an artificial being that does all the things that we humans can do, right? So it's an embryo, of course, grant you that, but this contains the basic element to do that. Of course, it's wrong at that time, at least. But I will show you the current deep learning revolution is not far from it. It's actually using exactly this architecture. Okay. Well, that's a story that later told. Of course, this is such a big statement. Of course, would attract a lot of scrutiny. And one of such very famous scrutiny was provided by people like Minsky, right? So basically, Minsky would say, okay, you say it's so powerful, let's try to use it to do something very simple, right? But of course, he's looking at just a single layer perceptron, right? So not single, two layer, input layer and output layer. He want to do a very simple logic operation, namely XOR, right? He want to distinguish the two black dots, two field dots with the two white dots. If you look at the operation of the neural network, it's quickly become clear. You just want to put a line through these 4 dots so that you can separate. To the left of the line would be black, would be filled. To the right of the line would be hollow, right? And you cannot do that with a single line, right? So he uses argument like this. For example, the book he wrote, it's called Perceptron, actually uses this example. Can you design something to tell the difference between the Swiss roll, right? So can you do that? Challenge it. So of course, you cannot do it easily, at least at that time, with a one-layer perception. But people also know that. For example, in the case of XO, you can easily achieve that with one hidden layer. If you have more than 2 layers, in the middle you put a hidden layer, you can do that. You can do that. Then he challenges, okay, can you do more complicated thing like this? So there's no proof that you can do anything you want with this architecture. So that was the start. That was actually sort of killed the first wave. It's so-called the first AI winter. It's very, sort of, Minsky has a lot to do with that. There comes the second wave, which is, what gets physicists excited about this. In the early 80s, I will not talk about Boltzmann machine. I'm talking about mostly about Hopfield model. In the early 80s, I think Hopfield came from a different angle. That's why he's awarded the physics prize. He came from the angle of physics. But he's tackling also a different problem. He's tackling the problem of the so-called associative memory. Meaning that, okay, in the neural network, I can encode certain information by the firing pattern of the neuron. So I have n neuron, the certain, even for binary neuron, I can have 0, 1. They are arranged a certain way. I call it the cat. It's encoded there, right? A picture. Then the idea is that the question is, then I have as my input, the red dot y. So these are the blue dots are the encoded state, right? These are, each one correspond to one particular state. So now I have another input y that's neither of this x1, x2, x3. Can you actually say, well, it's a particular x with some defect in your bit, right? So if you have a bit encoding for an array of bit encoding for a particular image, and you erase some of them, or you change some of them, have something happen, that some mistake happened, can you recover the original image by using a neural network, right? That's the question. And the answer is yes. And the model he devised to do this is the so-called Hopfield network. This is how it actually operationally works, right? So you have a bunch of neurons, and in this case, he even simplified it to be a binary neuron. Namely that the output of this neuron, or the x or y, the output of the neuron is either 0 or 1. Okay? The state is, it can either be 0 or 1. It's very simple to think about it as a physicist, because that's just the spin, right? Spin up, spin down. There's 2 states on each of the neuron. Now, he did then implemented a McCollum-Pitt type of neural network, even also simple. Basically says, well, okay, I sum up all the input to a particular neuron I, and sum up all the input from other neuron J with a weight that lives on the link between I and J, right? Wi and J times the activity at J. I sum them up, and I go through this nonlinear function. This nonlinear function also is a very it's a sign function. Basically, take look at the argument of this function. If it's positive, then it's plus. If it's negative, then it's -1, right? So it's the 2-bit is -1, +1 and -1. That's the 2-state. So you just iterate this process. Of course, iterating this process, the dynamics of this process depends on Wi and J. So the question then becomes, can you find a set of weights, Wi and J, that allows you to achieve associative memory, meaning that there are these encoded, the state encoded by a combination of X, and if you make some mistake, eventually it will flow to the closest one, the one that have the so you recover, you associate Y with the corresponding correct X. Long story short, so he actually also have a lot of inspiration. At that time, he's actually going to neuroscience. So he did his other things in biology, and then he was actually interested in neuroscience. He says, well, okay, this problem has been solved by sort of having a neuroscience solution to this. Basically, it's the so-called Hebbian law, meaning that, okay, what wires together, fires together. How many people know about what Hebbian law is? Hebbian learning rule, okay. Hebbian learning rule is, say, in our brain, of course, in any real neural network, you learn by updating these weights, synaptic weights, synaptic plasticity. And then how do you update them? One particular way I think is very popular and probably one of the dominant way of updating the weights is through is hypothesized by Hebbian, but later on have experimentally tested to be true, is that if two neurons are firing and their firing pattern is such that they're firing together, meaning that their firing pattern have highly correlating time, then depending on the order, if A fires before B, then A goes to B as it's strengthened. If A fires after B, then the connection between A and B is weakened. So that's so there's a Hebbian law says you update, you move, you change your weight according to the firing pattern of the two neurons that this link is touching each other, right? So he basically says, let's do that. I know he has other reason to believe that this is a lot of intuition building in. He says, well, let's say Wij is the two neuron firing pattern, two neuron firing activity, Xi and Xj, multiply each other, and you sum up all the patterns you wish to store in the system. That's sum over mu. Mu goes from 1 to P. P is the number of patterns you want to encode in the system. And then you can easily show that this is a good way to do it. If you have one pattern, very good way. If you two pattern, if you place them apart certain way, you can also do it, and so on and so forth. So he actually was able to show that there's certain capacity. So this will show you that first, you can recover the stored memory. And second, I think this is something he alluded to in his paper, but later on proven more rigorously by Daniel Amit and Sampolinsky and Gottfried in this very famous 1985 paper published in a PRL, so very well known in physics community, but totally obscure in machine learning or neuroscience. But they show that the capacity of a neural network, of half-field neural network, scales with number of neurons linearly. Okay, so basically, if you can put in as many as 10%, 0.14 times n number of patterns without them having strong interference that you cannot tell them apart. Again, why is physics so important? Well, okay, so in some limit, for example, Wij is equal to Wji. This is actually coming out of strictly out of Hebbian law, right? So that because it's a product of two activities, so the swapping them doesn't change, right? In terms of neuron activity. So if you have Wij equals Wji, you actually can write down the system as having a Hamiltonian. In other words, the dynamic, the iteration, the updates really follows a downhill dynamics of this energy functional H that defined on the space of X. So all the minimum on this energy landscape are the memory you try to encode to the local minimums. And all dynamics does is that if you start somewhere, let's say a little bit away in the valley of the defined by X1, you will go to X1, right? If you cross that barrier, if you're on the other side of the valley, then you're closer to X2, then you go to X2. Now you can easily appreciate intuitively, if you put more and more these dots, this minimum into your system, it becomes too crowded, that there's no separation between X1 and X2. That defines the capacity of the network, right? So that's, okay. So, but suffice to say, so this, people in the statistical physics know immediately that this actually corresponds to some kind of spin glass. So in other words, these are Ising model, but with the coupling between different spin having a random value, or having some only have some statistical property instead of having them to be a constant. So in the spin glass model, you can all these problems about the capacity, about the capability of the dynamics to reach certain minimum, certain solution has been studied. And really spin glass theory played a huge role. Spin glass is a theory in physics, played a huge role in both the original motivation. If you read Hopfield model, neural network, spin glass was actually one of the motivations. There are two things going into it. One from neuroscience, Hebbian learning rule, one from spin glass. These two together gave rise to this Hopfield model. And also following on the proposal of Hopfield model, the subsequent solution, that understanding of the Hopfield model was also achieved through theories like replica symmetry breaking, replica theory, and so on, by applying those techniques in physics and into the on Hopfield neural network, and a lot of the property like capacity and so on was solved using technique from physics. So I think, at least for me, there's no doubt this is a physics prize, right? The connection between statistical physics and Hopfield model as a machine learning paradigm is definitely deeply rooted in physics. So if you look at a Nobel Prize website, you find this picture to the left, right, which I just described to you. There are these different valleys and different minimums. If you drop a ball, that's initial, so your damaged image or whatever, and eventually will fall to the final state. That's the recover. So to demonstrate that, on the right, on the top, you have only part of the image, right? The head of the bird, parakeet. And if you run the simulation, you run the dynamics, it will recover the full image. Of course, the full image was already encoded in the weights, right? As one of the images you want to, in the W, you already encoded in. And same goes here. If you just have a grainy picture of of a boat, then actually you can recover it just by running, the dynamics of this model. But again, all the information about the correct image has been encoded in the weights. Okay. All right. So why is Hopfield model important? I think Hopfield model, that second wave also died because Hopfield model has limited application, right? It does do very well with associated memory, but you cannot do classification very easily. You cannot do many things. Even though it has a very beautiful theory behind it, the model itself the capability is limited, right? But it taught us a couple of things. The first is that actually dynamics is computing. So the system, a physical system, you go from one state to another state, following some rules. That rule could just be a physical rule, so allow you to find the minimum. That rule can also be a rule of learning that allows you to go to a place that you actually achieve certain function, right? So that's number one, that dynamics can be, we can think about dynamics as computing, right? That's number one. Number two is what I really like. the half-wave model really exemplifies a very deep connection between machine learning and physics. I don't know. People probably have said this before, but I don't know if anybody said that. I claim I said this. Learning as an inverse physics problem. Why is that? A physics problem, take the spin glass model, right? Physics is, I give you the link. I give you all the W. It has some distribution, it's random. I want to know the dynamics of how X evolved, right? I drop the Y here and it goes in the X space, in the neural activity space. And you figure, so all the spin glass theory and so on and so forth is about that, right? Machine learning is actually the opposite, right? It's inverse problem. I want this initial condition, right, Y, to go to a particular place. I wanted this to go to there. I don't care how you do it, just do it. But at your disposal are these interactions, this W, right? So instead of looking at dynamics of X, you can adjust your W, your interaction, so that it will guide you to the final X that you desire. Okay? So to me, that's an inverse problem. As you see, that it's in some sense it's really an inverse physics problem. Okay. All right. Now I said the first wave, the second wave. Now go back to the final wave, which is what the main topic of today's talk is show you some of the things that we did that try to understand what deep learning, or well, I'll tell you what it is. Okay. Now remember I told you that the first wave is really the first development of neural network and the perception architecture. What is perception architecture? Very simple. You have the input layer, you have hidden layer, many of them you can be, and you have output layer, right? All the way connecting, so there's no feedback, there's no feedback. There's always feed forward. So this is a not fully connected, but it's a feed forward perceptual model. Basically, it's connecting the input to output in a one directional way, right? That's the architecture. But that, if you look at all the modern deep learning architecture, that is it. So modern neural network architecture have the same architecture as a perception, right? You have input, you propagate the next layer and the third layer, and so on. Why is that so good? It's good for a couple of reasons. One thing, predominant thing, is that it allows you to do back propagation. It allows you to a very easy, straightforward way. Any high school student, any middle school student can do this. You have an initial guess of the weights, right? You propagate through. At the end of the output, you say, do you agree with the prediction? Does it agree with the right answer, right? By how much? It doesn't. So you have the difference between the right answer and the predicted answer. Let's say people call it loss function, right? So the loss function is finite, means that you're not close to the right answer. Then what do? You just change your way in a direction that go downhill. Try to minimize, or not minimize, even minimize, just descending on this. Basically, it's that if I move this direction, would my loss go down? Yes. Then it go that direction. So this is called gradient descent. And gradient descent is very, very efficient in this layered feed-forward network. Basically, you have this first layer, the output layer. You're not satisfied, right? Then you propagate backwards once. You get how dissatisfied you are in the next to last layer. And the next layer weight, you just update because you have a dissatisfaction at the next to last layer, and so on and so forth. So you can propagate by chain rule. You can do this layer by layer, very simple. And you cannot do that if you have feedback. If you have loop, that's all bets are off. You have to do annealing to make the process consistent with each other. So this is a very, very sort of a computer science driven approach, that the feed forward neural network is very, very simple. But why do we need that, right? We have all the clever people figure out a way even to do updates for feedback and feed forward, and that's okay, right? But the problem with that is that another problem is that in order for you to make any progress, you need a huge network, right? With a lot of layers, and each layer have many, many neurons. So if you look at how much computing time for you to do update with a feedback loop, it goes easily like a square of the total number of links. And if the number of links is gigantic, a square of that is totally infeasible. Whereas here, it really goes linearly with the number of links, okay, the computation. So that basically is I think the sort of the advance, the feed-forward neural network was invented more than 60 years ago by Rosenblatt. But what's new this time? That's the question we asked in our review article. And the answer is, it's really technical, right? First of all, they cannot train a large model because they don't have enough data. At that time, 1950s, they don't have labeled data to train. They don't have, internet to crawl. They don't have billions and billions. Another corresponding limitation back then is that they cannot train a large model, right? And large model is actually, very, very important. Think about the current day large language model. I was just listening to a talk. Says, oh, we train a small model with 10 billion parameters. Okay, that's the kind of, yes, indeed, a trillion parameter model is pretty normal, probably even on the smaller side, right? So ChatGPT, I don't know what the number is now. People probably know, but at the time I checked, was 6 trillion, you say?
670.
So it's okay. So it's still below trillion, but there are models that over the trillion number, right? So they cannot do that at that time. But fundamentally, in terms of architecture, there is some innovation. For example, there are architecture like CNN, RNN, LSTM. I think the most predominant, really new architecture is the transformer. But even for transformer, it's still feed forward, okay? Don't let anybody fool you. It's still feed forward neural network. You still do backpropagation to train your model, right? That did not change. What is really fundamentally changed is the amount of data, labeled data, and the size of the model, right? So as Anderson famously said, this is we resort to some just general statement, the more is different. So people ask, so you can ask physicists, what do you don't contribute any fundamental interaction? What's new there? So his answer, Anderson's answer, I say it again, and here too, is more is different. Here, it really pans out very beautifully that if you put more data in and you put a lot of parameter and compute go with it, something fantastic happens. Right? Okay, all right. But the bottom line is actually very important. It's actually like a salesman pitch, right? For us theorists, physicists. You see, the second wave, I think the theory is ahead of the model, right? Because you have spin glass theory already before the advent of popular model. So he has borrowed insight from the spin glass theory and then subsequently used techniques from spin glass theory to solve the model, right? Here, we do not have a theoretical foundation for deep learning. We just don't, okay? So that's a sort of a rallying cry for theoretical physicists out there. We don't know, so at least to the extent of sort of a spin glasses for half-wheel model, we do not have equivalent theory for the current deep learning neural network. Yet, on the other hand, as I told you, the architecture is actually very simple. So how do we go about to make some progress by building a theoretical foundation? This is sort of going back to what I really want to tell you about some of our own work. All right, okay. So this is the title of, other than the historical part, this is the real title, right? So towards a theoretical foundation for deep learning. So before I tell you that, for physicists, we are naive physicists, we don't know what do you mean by machine learning? So this is the sort of a 101 of what machine learning is, right? In my simple-minded way of understanding it. In my simple-minded biophysicist way of understanding, because biology have a central dogma, right? So they always have 3 blocks. 3 is a magic number. So The central dogma of machine learning, again, I said this, so I said I can label, I put my name down here. So has 3 blocks. In the middle is the most important, it's the model, right? So what the model does is trying to get a training data. You have a data set that you want to say, okay, this picture is a cat. This picture is also a cat. This picture on the other hand is a dog. So you want the machine, the model in the middle, to then to actually give the input, give the right classification of this image, right? That's basically what it is. So from a training data to go to a model that correctly predict the training data, correctly capture the training data. That's the first step. But that's not enough, actually far from enough. A good model will be able to say, well, okay, you can predict all the training data. All the data I give you, you can answer it correctly. What about, I just hold back the answer. I just say, okay, I have a new data coming in. Only give you the input. Would you give me the right output? That's prediction. And that's what people call using test data. So these are data probably belonging to the same statistical distribution of the training data or in adjacent to it, right? So to test whether some kind of transfer learning happened. But anyway, there's a test data which really tests the goodness of the model. So the first step can be done by optimization. As I said, once you have the training data, you can construct a loss function, right? So you say, okay, I predict something, and whether it's true or not, you can compare with the true answer. If the true answer is different from the predicted answer, you try to move your weight so that you can actually go downhill in that loss function. So you do optimization. You do have a function to optimize, right? So that you can do optimization, various tricks you can do. The second step is called generalization, meaning that once you have a model, how generalizable to other data that you have not seen before? Is your solution also correct or also apply to a situation that I have not seen before, the data you have not seen before? Okay, so from going to finding a solution to find a good solution, there's a lot of, so I will tell you a little bit more about that. That's what people call regularization. Again, it's 3 blocks, right? So you have optimization, you have generalization, you have your regularization to go from a solution obtained from optimization to a good solution. So I'll tell you what I mean by that. So there's already 2 set of key questions. One is learning dynamics. How do you find from some initial guess of the weight to actually finally find a solution, right? That's the first part, optimization part. I call it dynamic because it's the process I'm interested in, not just the final result, right? Optimization usually doesn't care too much about dynamics. I do. The second is generalization. How generalizable? Suppose you find a solution. How do you judge this solution is a good solution or bad solution, right? Instead of doing the test data, just sort of crank it in, you actually have some general feature of the solution that you know will give rise to a better solution. Okay, so I probably won't have time to talk about the second part, but I'll tell you the first part, something about the first part. So before I go on, I also want to show you some differences that I think is very important to realize. On the left, it's a very difficult problem in real space, meaning that if you want to know a protein structure based on their amino acid interaction, not AlphaFold. Okay, AlphaFold is not physical. So if you want to know how protein is folded, and you look at the configuration space, in the physical space, there's a free energy landscape. The native proteins sit at the minimum of the free energy landscape, right? Remember, this is a very high dimensional space, right? Each amino acid has 3 coordinates, right? So you just, and more, there's a side chain and there's also. So there's a very high dimensional space. You want to find the minimum, and there is the minimum, native structure. There are many local minima that you can get trapped. So if you want to do the protein folding problem, it's a very, very tough problem. And it's tough for a reason. The reason is that there's only one solution, or very few solutions. There's a true native protein structure. There's a true unique solution to the problem of minimizing the free energy. Okay? So finding it in a very high dimensional place is tough. Machine learning more like look like this. I mean, if for development people, this look like a Washington landscape. But yeah, so we got that insight. But anyway, so this is saying that, well, this is a loss function landscape. And the space you're looking at is the weight space. Remember, the number of weights, even though the number of coordinates in the physical space is huge, the number of weights is even larger, right? So this is even much larger space. And in this, because you have so many parameters, minimizing this loss function based on the training data, you can find many solutions that set at the minimum. There are many minimum in this landscape. This landscape, by judging from the loss itself, is highly degenerate. In other words, there are many choices of weight that give you perfect fitting for the training data. Okay, so because the dimension is so large. And you want to do that, that's the beauty of the current neural network, is you can afford to do it, right? And you want to do it because you don't want to be in that situation, in protein folding, that's very hard to minimize the system to find a solution. So you can easily find a solution. Not that easy. Well, I tell you, how it does it. But the question then it turned around is that among all the solutions, which one is better? Better in what way? Better in the sense that, okay, this is a loss landscape for the training data, right? So of course it depends on data. Now I give you a test sample that is not part of the training, right? Then look at how well it performed on those test data. Which solution, which of the three blue dots on the right-hand side, you think will do a better job? Any guesses? It's the one that's, okay, middle, okay. So why is the middle? Yes, so you're absolutely right. So why okay, so of course this is a highly simplified picture of having one dimension, right? So what you said is absolutely correct in the very high dimensional space, meaning that you have you have n directions, right? So you have n such flatness, right? So the more flat direction you have, the better, because your solution is only constrained by a smaller number of hard constraints. So you're more likely to be generalizable because some changes may just correspond to the soft direction, some changes in data that wouldn't affect your performance, right? That's basically the general idea. Okay, so I will not tell you that the second part is all about that, why the shallower solution is better. There are other criteria go together with the sharpness. So if you're interested, I can give you a reference. But I will tell you so now the first question becomes interesting. Suppose you want to go there, right? You want to go to the flat. Suppose given that the flatter solution is better in generalization, and you want to go there. There's no reason why you should go there, and better than going to the sharper one. Why should you do that? They have the equal. They are equal in their loss. So I'll tell you the first part of the talk is it's published. So if you want to know the details, you can go check out this paper. It's stochastic learning dynamics in deep learning, descending down a fluctuating landscape. So the title of the paper is very technical, but it shows you the inverse variance flatness relation in stochastic gradient descent is critical. That's the latter part is most important for finding flatter minima. So explain to you the first part, the inverse, what do we mean by inverse variance flatness relation? What is stochastic gradient descent, right? But the most important part is that this particular algorithm, SGD, allows you to find a flatter minimum. Okay, so here we go. I guess I have 15 minutes. Okay, all right. Talking about toy problem in machine learning. This is the toy problem in machine learning. At least for physicists, people think in machine learning, yeah. Like I said, the horse has been beaten to death many times. We don't care. It's dead. We care about we want to find out how the horse actually died, right? How do you find the solution? So this is the example we're going to use. So what it is that at the top is the input layer, right? So these are really just the values of the pixel by pixel value of the flattened 2D image of a digit, right? 1, 0, 2 to 9, right? On the top left-hand side, each image is a handwritten digit. So the two will vary from each other, right? There's 6,000 of them for each digit. So total, you have 60,000 such images. And each image have 28 by 28, 784 pixels. That's the dimension of the input layer, okay? And then you propagate through. At the end, you have 10 output. If the number 1 lights up, that's a 0. If number 2 is the highest, that's a 1. So that's your call, right? And you compare the call with the actual answer in the training data, and you construct a loss function, and you just try to minimize that loss function to determine the weight that allows you to do this prediction, this classification task. That's basically what it is. So, okay, now, why is the prediction? For sample K, the input in that input layer is x of K, the vector, right? X of K. Theta are all the parameter, all the weights in your neural network. Right? So the prediction is y equals g. G is the function that's captured by this architecture, right? You have layer by layer. So basically the output y, the predicted output y depends on the input and the parameter. You want to construct a loss function. Basically, it's the difference between y of k for each sample and the difference between y and k and z of k. Z of k is actually the true answer for sample x and k, right? So you have some distance measure. So usually people use so-called the cross entropy loss. Basically, it's this vector output, how it overlap with the correct vector. So what do you do updating? So you have a loss function. The smaller, the better, right? So that's for sure. The smaller the L, the better. You want to go smaller. So what do? You go simple. So for the weight I, theta of I, every iteration, you just change in the direction that lowers L, the steepest way, steepest direction lowers L. You look at the gradient of L with respect to that particular weight, and you just move that amount. And alpha is a learning rate, right? For learning rate. So you just do the iteration, right? So, okay, that's all fine. But it turns out to be very clumsy. So the L is constructed by summing up all the data. So M can be astronomical, can be huge. In this case, 60,000. That's the smallest data set you can ever think about. But millions, when M reaches millions and billions, it's unattainable. I mean, you cannot just calculate L every time you want to do an update, right? So here comes another trick. So, okay, we cannot do that. What do? So why don't we select every iteration? I just select a subset among the capital M, a million or 60,000 here. I just select randomly 10 of them, 10 images as my input, right? I sum up all these 10 but randomly chosen. So every iteration I use up 10. So of course, after whatever 6,000 steps, I actually cover the whole data set. So after time, I will cover the whole data set. So the time for it take to cover one data set in the jargon, in the business is called the epoch. Each time you actually capture the whole data set is one epoch. But each epoch contains many, many steps, right? Okay, so okay, fine. You can do that. So that's L of mu. Mu corresponds to a particular subset of data, right? Mu is random subset of size B, batch size. So still go downhill. The theta dt is equal to minus alpha gradient of L, but every iteration, you have a different mu, different subselection of sample, right? So L of mu, of course, different from L, which is the average over all the ensemble average of L of mu, right? So the difference. The gradient of the difference going to the noise, what I call eta, right? So this again, I can write it as a physics style model. This is nothing but a long-join equation, right? With a simple deterministic part and the noise part captured by eta. So if eta is just random white noise, it's a Brownian motion, right? In the potential. And the distribution would be Boltzmann. So that's why people think, it's Boltzmann. Wrong. Okay, so you write it down. The noise, the average noise, of course, is 0. But all the information is being captured by the covariance, right? The covariance means that if I have some changes in some direction, and the changes in other direction may be correlated with that. So there's a lot of structure in the noise. For example, Cij is a matrix that capture the is a covariant matrix, right? So you find that in the physical system, like Brownian motion, Cij is everywhere the same. Everywhere in the wave space will be the same, and there's different direction are uncorrelated, right? So it's isotropic, and it's homogeneous, right? That's the formula there. However, so eta, the SGD noise, I call it SG noise, we define up there, is neither homogeneous nor isotropic. If you sit at one point, you look at the noise, it has a very distinctive spectrum. It has very, in certain directions, very strong, other directions, very weak, right? And also it depends on where you are. When you close to the solution, the noise becomes smaller. Okay, so it's neither homogeneous nor isotropic. Well, that's physics, right? So if you imagine a physical system was driven by a deterministic force, gradient of L, plus this funny looking noise, you can map to a physics problem. So I call this the learning particle. So you can think about a particle with coordinate spanned by all the weights. That's a particle which moving in this landscape of L, but jiggle around by this funny noise, right? In this very high dimensional space. So, okay, that's what I say. It's a high dimensional drift because you have a deterministic term. Drift diffusion with funny, non-homogeneous anisotropic noise. Okay, it's a physics problem in the artificial world, let's say, okay, in the AI world. But it's a physics problem, you can map it to using Landry equation. It's fine, okay, so that's not much insight, right? By the end of the day, by the end of 10 minutes, I'll tell you this. This is not a high dimensional, it's a very low dimensional space, much smaller than the actual number of weights. And the funny looking noise is actually very, very smart, allows you to find the flatter minimum. Prefer the flatter minimum than the sharper one. Okay. So I give you the take home message. So how do we know it's a low dimensional space? Okay, so we know how to determine that. Remember in the thermodynamic class, statistical physics, each dimension capture 2k, half of kT, right? Half of kBT energy. What is energy? Energy is V squared, right? It's the variance, because mean is 0. So each dimension carries the same amount of energy, okay? Clear? Do the same thing. You can look at the fluctuation in the wave space. You can do PCA, basically the fluctuation in different direction, right? And you find that PCA spectrum is not flat at all. It has very large, only a few modes capture all the fluctuation, right? In other words, if you look at the total amount of fluctuation captured by the top components, it quickly reached 99%. So 99%. So this is in the 2,500 dimensional space. Not hugely large, but it's pretty large. All the fluctuation, all the all the fluctuation happened in the top 40. 99% of the fluctuation happened in the top 40 dimensions. Those are the dimensions you're actually learning. You don't care about the other dimension. Okay, that's about the dynamics, right? The noise part. What about the landscape? Remember, I have two parts in my Landry equation: the deterministic part, which is determined by the loss function, at the noise part, which determine the actual fluctuation. So I told you about the fluctuation part. Let me tell you about the landscape part, the L itself. For a smaller data set like this, we actually can look at the L, the shape, right? So you can look at the L. And you find that near the solution point, you can also the PCA, principal component analysis, tells you a coordinate system. And it is this coordinate system we look at the landscape. So let's say we look at around PCA top 100 direction, the 100th direction. We cut across this high dimensional landscape, and it looks like a problem, right? Look like this. It's very smooth. And if you look at that direction, and the bottom is the some very minimum value, and you say, how do I define this landscape? Well, I want to know the flatness of the landscape. The flatter it is, the more. So I define using F. What is F? F is how far I have to go away from the middle in order for my loss to increase by a factor of 2. Okay. So all right. So that's just arbitrary definition, but it's a uniform across. Defined across all the directions. So I call this a flatness. So the bigger the F, the flatter it is. Okay, I can use Hessian, but Hessian at this particular point may have some little noise. Will actually even have negative value. That's why we choose this sort of a non-linear, non-local definition of flatness. Okay, so this is a well-defined definition. The bigger it is, F, the bigger F is, the flatter the landscape in that direction, okay? So I have 2 numbers in each direction. One is the fluctuation of the weights in that direction, the variance. Another one is the landscape flatness, F, right? So I calculate both, and I get, so for each mode, I have 2 numbers, right? Top is the flatness, bottom is the fluctuation, the variance in that direction by using PCA. Now I see one goes up, one goes down. So what? But if you plot one against another, you should immediately jump up your seat. You didn't. Sorry. Why? So this is telling you that the flatter it is, the smaller the fluctuation. Is that weird? It's counterintuitive. It's totally weird. It actually directly breaks down a fluctuation dissipation theorem, directly violate the Einstein relation in equilibrium system. But that's, yeah.
I think it's the other way around. Isn't it kind of obvious that it should be like that? Because you're doing gradient descent. So at each step, you're multiplying by the gradient. The fact that it's flat means the gradient is small.
Yes, that okay. So you are one head of ahead my slides. So that's exactly, so in other words, the noise is not the white noise, doesn't have a constant strength. It goes back to my original observation that the noise is anisotropic. In the direction that the landscape is flatter, the noise is also smaller. Because the noise is the fluctuation of the gradient, which in the flatter direction, the value is just overall very small, right? So that's okay. You already give the answer to the puzzle, but the puzzle, nonetheless, this is actually capital I in the first place, right? How could this be? Because normally, so this is the sort of our physics training tell us this, right? So if you have some thermal fluctuation, so the eta is noise with a constant strength, like a thermal noise, right? The Brownian motion thermal, and the Brownian particle lives in the potential, then you can calculate the fluctuation and its dependence on F, and you get the fluctuation is proportional to F, right? Sigma square is proportional to F squared instead of inversely dependent on F. So that's why we call the inverse Einstein relation. So Einstein will say, it's going the other way. So anyway, okay, it's for fun. So this is the actual intuition you provided, which is what we tested, indeed is true, is that you cannot think about the noise as just random kick from the environment. It's not. It's coming from the fact that each one of the L of mu is different from the other. And it's also therefore different from the mean. So the correct physical picture is that you have a fluctuating landscape, right? And the difference between different mini ensemble, we call it, mini batch, the landscape contributes to the noise. So the noise has a lot of correlation with the overall landscape itself. So we tested that, and we show indeed the noise strength actually is highly correlated with the Hessian, right? So the smaller the Hessian, the smaller the noise. So if you look at the covariant matrix, and the Hessian or the loss landscape, these are highly correlated. They're not commutable, but they are they're slightly off to each other. This is another ongoing thing that we're working on. Actually, there's a very interesting thing. Then people in the community think that maybe just directly equal to each other. They're not, but they're highly correlated with each other with some sort of almost like a power law dependence. Okay, that's a sort of a detail, but this is the essential ingredient, essential insight, right? So the noise is not thermal noise. Also noise will depend on where you are. The homo is inhomogeneous, meaning that as you get closer and closer, as you progress in your update, you're getting closer and closer to the minimum, the noise also becomes smaller and smaller. So this almost looks like an annealing process, right? So this is annealing, meaning that you have to, but you don't do an annealing schedule because the reason you become smaller and smaller because the curvature becomes smaller and smaller, right? So because and the gradient itself, the average becomes smaller and smaller as you approach the final solution. So I say smart noise in SGD is almost like a self-tuned annealing algorithm to find flatter minima. But why flatter minima? So I didn't say too much, but see, the noise is larger if you compare in two minimum. One has more sharp direction than the other. Then the one has more sharp direction will have a higher effective temperature than this. So even given they have the same free energy, even just using normal standard statistical physics, if your temperature is higher, you affect your minus F over KBT, right? That will be becoming, because so you can look at the preference and you get a term that it will prefer the lower temperature one. Because the low temperature one will have an effective F over KBT will actually be larger, if a negative sign in front. So that means actually, you can have more probable. Okay. All right. So we can actually this is our empirical result. We have some explanation based on, analysis and local, so it's sort of a semi-rigorous way. But in a simpler system, so you can look at the system that do indeed have a degeneracy, but degeneracy is broken by, so you have a situation where along the valley, the loss function is the same, but a different part of the valley, the curvature is different. And you actually do SGD on that. You find indeed there's an extra term coming from the effective loss, coming from the curvature, flatness, F, that actually lowers the effective loss at the flatter side. So that you can do more rigorously by solving the Fokker-Planck equation. But that's just added. Okay. So I'm basically concluding this first part. Don't worry, I won't go to the second part. The deep learning neural network, it's really a low dimensional learning dynamics in high dimensional weight space. The low dimensionality comes from the fact that those are dimensions that relevant to the data. It's governed by the data. So you say, why 40? Why not 100, 400? The dimensionality is really, the system allows you to actually freeze out all the relevant direction. It only focuses on the direction that matches the complexity of the problem. For example, take MNIST. If you want to separate 10 digits, you need 20 to 40. But if you shrink it to just want to distinguish 0 and 1, the sharp direction shrinks, goes down, meaning that it doesn't need all that. So all the rest it just become reserved for other tasks or just be flat. So it really reflects this wonderful property of this very high, even though high dimensional space, but was able to freeze out the redundant, the useless dimension. So it only go into and that is done by SGD, by the effective temperature. Also unusual relation between weight dynamics and loss function. So this is sort of why SGD is capable of finding the flatter minimum. So that's also I told you about. I don't want to. Okay, take home message. I think the statistical physics is sort of, especially non-equilibrium physics. I mean, this is totally non-equilibrium, right? It's actually critical for building a theoretical foundation for deep learning. And on the other side, I think deep learning really provides a very, very big, huge playground for us physicists to actually look into the details of how the mechanism, right? The foundation, the mechanism, how does it do it? How does it learn? How does it forget? How does it interfere with each other? So it's the kind of question you ask in the days, the second wave, where people use spin glass, theory to actually try to ask questions about Hopfield model. You can sort of use physics approach to ask questions and answer those questions using physics. But so that's sort of all captured in this thing I already told you about. So go back and forth between physics and machine learning. I didn't talk anything about the physics, how it can benefit from machine learning, the sort of physics-based machine learning models. I don't have time, but certainly this is something we are having fun, and we continue doing that. But some future directions, I think there's plenty of to do. So this is really a rallying cry for physicists, especially statistical physicists, who actually go. Don't be afraid, right? So you're not going to catch the wave of large language model. They're gone, okay? They're gone. You're never going to catch them. But that's a good news. Good news is that you can actually, the dust is going with them, okay? So you can actually settle down and do your, fundamental research about understanding what's going on. Okay, thank you.
Couple of questions.
I've noticed in the physics community that there are some people who fully embrace the idea of machine learning, and there are others that have an existential crisis with it. What do you say to the people who don't embrace it? What do you say to them?
They don't embrace based on religion, then that's not good. If you based on some deep understanding, then I would like to listen to that, right? I think people are very emotional when they get to this, right? Okay, it's essential, they're going to replace us. Like in the workplace, people say, oh, AI is going to replace all the people in the IT business. Is that really true? I don't know, right? So it's a lot of fear. If I think physicists, probably majority of people would just don't understand it well enough to actually, they are afraid. That's my personal opinion. So my attitude would be say, oh, if you cannot beat them, you join them, okay? But you try to beat them. You start to say you are full of this and that because this is not good.
Very nice talk, really enjoyed it. So there is the physics aspect of this drift diffusion dynamics in weight space and understanding. But in terms of application, it seems to me that you also have come up with an algorithm using the mini batch to find the flatter landscape that's more easily generalizable. So if you then use this algorithm, you can go back and do this back substitution for all kinds of applications. Is it more efficient? And
yeah. No, by the way, we didn't develop SGD. But SGD is funny. SGD was really, I told you the history. SGD was developed because they did not have enough compute, right? So it was developed for convenience. Although there's some theory, but the mathematical theory is really about, this mini batch will not allow the system to diverge. As long as the system size is large enough, it's okay. It will find a minimum. But they didn't realize it will not only find a minimum, it will find a better minimum in this high dimensional space. So once we realize that, we can design it. We can design it better, right? For example, you can increase this noise by increasing either the learning rate or shrinking the batch size. So those are things that you can play with. But of course, you have other boundaries. Like if you increase your learning rate too large, you're going to be diverge. You are really indeed going to diverge, right? So you want to push against the boundary where you don't diverge. You rather sort of live in the critical space. But that's also problem specific. So we're trying to develop, now that we have this insight, we can develop a better sort of controlled. You're throwing some noise by controlling. You introduce some landscape dependent noise, not in the sort of a serendipity way, but sort of controlled way. I'm not sure that will actually lead us. At least we have a goal, so we can find out. So that does lead us in the direction that was never was thought of as a technical advance, not as indeed a very good regularization allow you to find flatter meaning. Yeah.
I think there was a question. Yeah, the question about the role that nonlinearities play in physical models, like your G function.
Yeah.
There's different kinds of nonlinearities you can have in a network, like ReLU, tangential, you have like dropouts and pooling layers.
Right.
Do you account for those, like, is some kind of potential barrier for the wave differential, or?
Yeah, we didn't play too much around. All of these are ReLU, right, which people usually use. We have not used other things. But the dropout is an interesting thing. You mentioned dropout as a way of introducing nonlinearity. But dropout is really, for me, is more of like a regularization to control the overall. You can think about it as introducing some kind of noise, right, in the system. Because every iteration dropout is different set of weights, right? So I have not worked it through, but I think it may be able to relate that to some of these good character. Why does it find better solution? Probably can relate back to whether it's actually finding better solution. Another sort of ingredient, another good characteristic of a solution that makes it more generalizable is the size of the solution. You want to have the weight just smaller. So to have a dropout and you train the rest of the weight probably allows you to find a smaller solution. So we have to do a little bit of empirical study, and we find the dropout is actually interesting because you probably know this. Dropout has a hyperparameter, the fraction of nodes you drop out. And it turns out your dropout is good. Some dropout is good, but a lot of dropout is not good. So there's a trade-off between, seemingly like the trade-off between you want to have a smaller solution, but you also want to have a flatter solution. And somehow some particular choice of a dropout fraction is optimal for doing both of them. Yeah. So that's, again, it's interesting. So see, we never want to study this until, and we didn't think there's something interesting until we tried it. So I guess the same goes here, that if we think dropout, we know dropout is a very effective way for certain things to make it more generalizable, we should study it in this fashion, right? So why not?
So thank you for the nice talk. So based on my shallow understanding, so the major difference between AI and human is that we can basically understand stuff, but AI cannot. Of course, you can say that the human understanding might be an illusion. And well, on the other hand, the evolution of mankind is that we learn things and we discover the like the loopholes or wrong things in the current knowledge, and we find new theory, right? That's the evolution of mankind. So in that sense, it's not saying that AI just cannot exceed people, because AI learning basically based on the trainer's perspective and the known knowledge of mankind. Yeah. Right.
Well, that's a good question. I think it goes back to sort of what are you afraid? Yeah. So I think AI has yet to demonstrate the kind of ability to generalize outside of sort of outside of its so data is there's a lot of data. So anything that actually exists in the literature, in the written literature or whatever in the web, it probably can digest it, and then using that to generalize and find some answer to it. So like a chatbot can give you answer about anything. But can you use that? That's actually a very good question. Can you use it to discovery? So that actually is a very important question for AI for science. Is there any fundamental reason why the AI architecture cannot be used to make new discovery from data, right? So basically, the idea is that if you have enough data and you have this machinery in between, you actually be able to, discover something. That's the question mark. There's a yes or no answer. If it's a yes, then how can you demonstrate in one particular case that can be done? If you say no, what is the fundamental reason that it cannot be done? So I think that's an open question. I don't know anybody has any answer to this. So this is very interesting. Like, even asking AI. So there are some fundamental laws in physics, like conservation, some conservation laws, some symmetry, that if you know, you can enforce it. But what if you don't know? And if the symmetry is only in the data is very approximate, can you discover those symmetry? Can you discover those conservation? That it's not obvious, not so once you know it, of course, you can build a model. Even that is already difficult. You can build a model to AI model to enforce those constraints. Tend to be very global constraints, which is make it hard to enforce. But even if you can do that, that's actually a little bit cheating. It's not discovery. It's really using some other knowledge to enforce, to inform the neural network. But a real challenge is that can you actually give data that they can discover, laws? By law, if there's a different level of design discovering law, you can actually have a neural network that can do right prediction. But law to me is that you have to be able to summarize the finding with very simple, with a few bits of information that allows you to write it down, right? You cannot say, oh, neural law can do these things, but have all these parameters. I don't know how it did it, it just did it. So is it agreement with existing data, prediction with existing data, agreement with that shows that you really understand, you discover something, or it has to be something deeper than that? You have to, so those are all open questions. Whether it's related to how human brain works, that's another totally different question. That we are trying to answer that question based on very simple tasks that people do, classification or, doing simple things. How does the brain works? We know at the fundamental level, brain doesn't work the same way as the feed-forward neural network in terms of architecture, in terms of what each neuron can do, and in terms of learning rule. Like backpropagation is not what neurons do in the brain. Neuron has, as I told you, in the Hopfield model, it's a Hebbian learning rule. It's mostly local. It doesn't know there's a global loss function you try to optimize. It doesn't. What it does is know locally there's two neurons, they fire together. Oh, let me strengthen the link. That's most of the time what it does. How does this give rise to, behavior as we know as intelligence?
So is it fair to say that at least currently AI cannot evolve by itself?
Oh, I don't know. Yeah, so yeah, going back to the New York Times article 1958. No, I agree, but it definitely doesn't reproduce itself, not yet. Evolution is another, I don't know. Yeah. Oh, yeah.
I think we should wrap up here. Let's thank the speaker. Oh,
One more.
I'm sorry. All right. We will get.
Thank you very much. It was very interesting. So as a developmental biologist and a
Yeah.
neuroscientist, it's fascinating. How this develops. But what actually struck me was your energy low points.
Right.
The memories and the energy low points. And you refer to Waddington,
Right.
who postulated that as cells decide what they're going to be, they're kind of going down
Right.
an energy, to a state of low energy. And, that's their final decision. Actually, Waddington was totally wrong. And cells go along their pathways,
Right.
but it's a very active decision-making
Sure.
process. And we know now that they have to be kept there. If you don't keep them in their final state, they actually will revert to somewhere else.
No, I totally agree.
So was when you had that flat
Right.
kind of sense in your model, I was thinking maybe actually that's what more like what the Waddington revised model should look like, where there's a kind of a flatness which allows a number of places
Right.
where the decision can go, where
Yeah,
that I think is much
absolutely.
more
No,
analogous
I
to
totally
cells.
appreciate that, because I think in this very high dimensional space, the flat direction is there for a reason. It's there for you to have a choice to make either development or a choice to do more things. So you have the, many, many direction you can move. For this, so I told you about this particular task. You find a solution. And you say, why do you need all the other dimension? You can just build a smaller model. No, because who says that your brain wants to do one thing? You want to do many, many different things, right? At least here, you actually can address question. This is sort of the part of the paper we talked about is a phenomenon called catastrophic forgetting. Is that when you learn one thing, and you put it there, and you start learning other things. In the current neural network, you will forget about how to do the first thing. So how can you avoid this? The way to avoid it is actually once you learn something, the sharp direction, which is a very few of them, you don't touch it anymore. But you allow the flat direction to evolve, to learn the second one or the third one. So in that case, then you would not. So all the functional or the functionality is captured by this very small number of dimensions, which you don't want to evolve that, because once that it disappeared. But you definitely have capacity to actually do more things in this high dimensional space. So I don't know whether analogy makes sense, but I think in development, yeah. Another thing I want to talk about, tell you that I really appreciate the landscape is not a static thing. It's kept there effectively by a lot of active process. There's a lot of energy to use to actually keep it there. So that's why I say, so in my other arm of my work, I work on biological system. One of the things I worked on is adaptation. Adaptive state looks, state that's just there, right? But it's totally a dynamic state. In other words, it keeps bouncing around so that it will just be there. If you turn off the energy, the other dynamic process will just fall dead. There's a difference between a dead state and an adapted life state. So, yeah, so that's basically.